Okay. Hi, everyone. Thank you for coming today. We are here for PhD dissertation defense for Dr. Hamid Gorji. This is his second PhD he's defending, and he will be talking for about 40 minutes. And after that, there will be one round of questions from the committee, and then it's open for everybody to ask questions. After that, I'll ask the audience to leave, and there will be second round of questions by the committee, and then Ahmed will leave and a decision will be made.
Okay, thank you. It's recording. It's recording. So, hello everyone. Thank you for being here today. And I would like to thank my advisor and my committee members. Actually, this is the third time I want to present this work for them. So thank you for your patience. And here's my PhD topic, learning-based framework for food safety, cleanliness, and data privacy. First of all, I want to talk about foodborne diseases. Unsafe food and foodborne diseases are significant global public health challenge. Each year, around 48 million Americans become sick, 128,000 are hospitalized, and 3,000 die because of the foodborne disease. And based on USDA, United States Department of Agriculture, the economic burden of foodborne diseases was over 15.5 billion in 2013, and this number increased to 17.6 billion in 2018, which is around 13%. And there are several sources of foodborne diseases, but here I want to talk about two main sources of foodborne diseases. The first one is meat and poultry processing facilities. In the United States, the foods that are most likely to become contaminated and therefore unsafe are raw foods of animal origin, like meat and poultry. And fecal matter and ingesta are two types of contamination on meat and poultry carcasses. Another source or sources are restaurant.
They cannot see the slides online. I don't know why.
Oh, we need to share.
Oh, yeah. Thank you, Shayan, for letting know we forgot to share.
Yeah, share all this screen.
Can you see Shayan?
Yes, this is great. Thank you.
Okay, sorry about that.
Here? We didn't want to miss a bit, Hamid.
Okay, so we are here. And another source or sources are restaurants and institutional kitchens. Restaurants and institutional kitchens can handle a wide variety of problems.
Let's make it small so they can see it.
So restaurants and institutional kitchens handle a wide variety of raw foods that can increase the risk of cross-contamination that can lead to foodborne diseases. And one of the main sources for cross-contamination during the food preparation stage is poor cleaning and sanitation. Currently, there are two main methods for contamination detection. The first one is visual inspection, the visual examination during the inspection. But this method is not that effective because we might have some sort of contaminations that are invisible or barely visible to the human eye. So the human inspectors, they can miss them easily. And another method is swab-based ATP, but this method also is not widely adopted because when you want to swab a surface, you can just cover a tiny area of that surface. Just imagine you want to swab a large facility. So it will be time-consuming and costly. So a more effective solution is needed to improve the current contamination detection methods. Fluorescence imaging can play an essential role in food safety and cleanliness assurance. It can provide fast and effective method for detecting organic residue-based contamination on different surfaces, the contamination that can be invisible or barely visible to human eye. Safety aspect, the company or lab is working with, they introduced a new technology, fluorescence-based imaging technology named CSID. CSID provides detection, disinfection, and documentation of contamination on different surfaces. However, imaging device like CSID or all other imaging device, they provide video or images that needs to be analyzed and interpreted to be useful for live inspection. These videos or images need an automation method for detection of contamination to make the decision-making easier for human inspectors. There are several studies. They use fluorescence-based imaging for finding the contamination on different surfaces like meat, like poultry, different types of vegetables. And many of them, they use thresholding method for finding the contamination on different surfaces. We also designed an experiment. We generated a data set based on various contamination biofilms like olive oil, like spinach juice, egg white, and we put them on different surfaces like steel, cardboard, wood, and plastic. Like all other studies, we also first tried to use thresholding method. We use thresholding method, and also we use a validation metric named dice coefficient. Dice coefficient simply says how well your segmentation model works. And we could achieve dice coefficient around 74% for that. However, there are some limitations and challenges. All these projects, all these studies, including our study, were carried out in the lab environment. And in the lab environment, you have a constant light intensity. And all these projects, they use fixed and homogeneous background. But in the real world, the situation will be different. The light intensity is not constant. It will be different based on the location. In here in this room, we have this light intensity, and downstairs, the light intensity will be different. And also, we might have some other objects in the background that can fluoresce in some levels. So determining the optimum value of threshold level in real-world environment is challenging. And inappropriate threshold level can cause false positive and false negative. So the first aim of my PhD is to improve the accuracy and reliability of the contamination detection and segmentation methods in the food industry. For the first project, which is about food safety assurance, we designed an experiment to detect fecal matter on meat carcasses, because the chlorophyll and its metabolites within the fecal matter can be detected by fluorescence imaging. For data collection, we went to 3 meat processing facilities in our state, in North Dakota. We used CSID, Safety Aspect Device, for data collection. We scanned 14 beef and 6 sheep carcasses under the supervision of a retired federal inspectors. He helped us a lot to understand
I agree. You know that USDA can join institutions
to understand the nature of the problem,
yeah,
where to scan, and which area we need to pay more attention. And here you can see some examples. On the left side, you can see 6 examples of the clean meat carcasses, meat surfaces. And on the right side, you can see 6 examples.
Whatever it is, John Paul, I'm going to.
Okay.
Oh,
Here. Okay. Please make sure you're on mute.
Sorry about that. Okay, so you can see the there's some contamination here. So with different colors and different patterns. And first of all, we try to use thresholding methods. And thresholding method, as I said, it can cause false positive and false negative. And in this case, you can see it detects a larger area than contamination. And on the raw frame, you can see the contamination, real contamination, or smaller than. So we try to use a more complex method. We use deep learning, specifically convolutional neural network for image analysis. For the first goal, we try to identify clean versus contamination frames. We use EfficientNet V0, which is an architecture, convolutional neural network-based architecture developed by Google. We tried that for classification between clean and contamination frames. And the total number of frames we used was more than 108,000 frames. We labeled them into two classes, clean and contamination. We use 70% of them for training, 20% for validation, and 10% for testing. And we could achieve accuracy more than 97% for differentiation between clean and contamination frames. The second goal of the project was to segment the exact area of contamination, fecal contamination. To do so, we use semantic segmentation. Semantic segmentation simply is a pixel-wise classification. First, you assign each pixel to a specific class, and then you classify the pixels. So to assign each pixel to a specific class, you need to annotate them. And for annotation, we use MATLAB image labeler. We annotated more than 55,000 frames. We annotated them into two classes, contamination and background. And here you can see some examples of the frames and their annotation. And the black is the background, and the white area are the fecal contamination. And for semantic segmentation, we use UNet. UNet is a well-known architecture for semantic segmentation. We use several validation metrics. And the main validation metric we use here is intersection over union. Intersection over union is an intersection between annotation and model prediction divided by union of these two. It simply says the percentage of overlap between annotation and model prediction. And we could achieve OOU more than 89%, precision close to 93%, recall close to 96%, and F-score more than 97%. And here in this figure, the first row, it shows the raw frames. The second, it's ground truths, the annotation by human experts. And the last row, it shows the model prediction. For example, number one, if you see my cursor, the number one, you can see the model could detect even two tiny areas of contamination. And the interesting frame is number 6. And if you can see here, we have a tiny area of the contamination, but our human inspectors, they missed to annotate that, but the model could find it. And we had lots of these frames that human inspectors, the human annotators, they missed that, but the model could find it. And let's see how our model works on a recorded video. On the left side, you can see the model output. On the right side is the raw frames. And after we segment the area, we pseudo color it, because by pseudo coloring that, you can make the visualization easier for inspectors. Because inspection is a time-sensitive work, it's under pressure work. You don't have all the day to inspect one surface. You might have several areas with contamination that you might miss. That is why after we segment the area, we pseudo color that to make it easier for human inspectors. And this is another surface. This is hand of that federal inspector that talked about. Okay, so already I mentioned two main sources of foodborne diseases. The first one was meat and poultry processing facility. We designed a project for that. And the second one is restaurants and institutional kitchens because of the poor cleaning and sanitation. That is why we designed the second project. The second project, which is about contamination detection in food service industry, we wanted to make sure for the cleanliness assurance, we designed this project. So we designed an experiment to detect organic residue-based contaminations on different surfaces, on a wide variety of surfaces, the restaurant and institutional kitchen. And here you can see some examples of the clean and contamination. As can be seen, the nature of the problem is more complex than the meat project, because we have lots of objects that can fluoresce in some levels. And this will make the work more complex than the previous one. And let's talk about the contaminations. The bottom left is some sort of contamination behind the freezer door handle, because we scanned the kitchen and restaurant, the kitchen and different surfaces. The middle one is the cutting board. It's a tiny area of contamination here. And this one is a toilet seat. So it's can be fecal matter, but probably not animals. So it should be human fecal matter. And for data collection, we use, again, CSID. For institutional kitchen, we visited 6 long-term care facilities. We scanned the kitchen, dining areas, and different surfaces. And for restaurant, we visited 2 restaurants in Los Angeles, California. And let's play a video to show you how we record the video. And this is a cutting board. And you can see some sort of organic residue-based, contamination on that. And this is another surface, another cutting board. You can see the contaminations, the patterns are different, the colors can be different. And in one of the restaurants, we had a small bar, so it's the countertop. You have some sort of contamination there. Okay, so for data set, as I mentioned, we scanned 8 facilities. The total number of frames we analyzed is more than 72,000 frames. And again, the first goal of the project was the identification of clean versus contamination. But this time we used exception model. It's a more complex model than the efficient net because we are facing a more complex problem. If I want to compare these two together, for example, the exception, the number of parameters we have is close to 23 million parameters, but in efficient net is around 5.9 million parameters. So this is a more complex architecture for dealing with more complex problem. And the total number of frames, more than 72,000 frames, labeled them into 2 classes, clean contamination, 70% for training, 20% validation, and 10% for testing. And this time, we could achieve accuracy more than 98% for differentiation between clean and contamination frames. But we had a main question. The main question that time was, we wanted to know how accurate our model is. When we take this device, we go and inspect a new facility. Because for all our processing, we put all this data together. We use the portion of them for training, portion for validation, and portion for testing. But we wanted to know how well our model can generalize when we take this device and we go to a new facility and scan it. To answer this question, we use leave one out cross-validation in the facility level, which means we use a portion of facilities for training and one of them for testing. And here you can see in our case, we have 8 facilities. We use 7 of them for training and one of them, Edgewood Vista, for testing. Again, 7 of them for training, Parkwood as a testing. And we repeated until all these facilities were part of training and testing. And here is the results. For example, number 1 is HOTAM, which means we trained on 7 and we tested on HOTAM. If we train on 7, take this device, we go to the HOTAM, we could achieve accuracy more than 93%. And same for 1212. If we train on 7 and tested on 1212, we could achieve accuracy close to 93%. And on average, we could get accuracy more than 91% for differentiation between clean and contamination frames. And for semantic segmentation, again, we use MATLAB image labeler for pixel-wise annotation, for pixel-wise labeling. The total number of frames we annotated was 12,000 frames into 3 classes: red fluorescent, green fluorescent, and background. So it's a multi-class pixel classification. And here you can see some examples of the frames and their annotation. You can see 3 different colors here: background, green, and red fluorescence. And this time we used DeepLab version 3+, again, because we were facing a more complex problem. So we used more complex architecture. And the main validation metric we used was intersection over union. And again, 70% training, 20% validation, and 10% for testing. And here you can see the results. This time we report mean OOU because we have 3 different classes. It's more than 95%. And also I split them into 3 classes, and you can see the OOU of each class. And in the figure, for example, number 5, it shows even a tiny area could be detected, could be segmented by the model. The model could successfully segment the green fluorescent, red fluorescent, combination of them with different patterns, so we could achieve acceptable performance. So I talked about 2 projects, about 2 main sources of foodborne diseases. The first project about food safety assurance in meat processing facility, and the second one, cleanliness assurance in food service industry. But now I want to talk about data privacy. We wanted to know how important the data privacy is to our project. Because the data-driven method, like deep learning, they need a large amount of annotated data, labeled data set. So this data can be collected from different clients. We go collect data, bring data to our server or computer for analysis. But this data may contain sensitive information like financial data, like medical records, like transaction histories, or like our inspection data, because we are collecting really sensitive data. Because based on this data, we can say a facility is clean or dirty. So if this data somehow leaks somewhere, so it can jeopardize the business owner's reputation. And another issue we need to take into consideration is data storage and computational resource. Because we collect video and collecting the huge amount of data, transferring and storing them is time consuming and costly. And also when we put all this data together, we can increase the risk of data loss. And also by increasing the amount of data, we need more computational power to analyze it. In addition to all of them, convincing the business owners to transfer their sensitive data to a central server is challenging. I personally was part of lots of data collections, and the first thing the business owners and managers, they were asking me, it was about data privacy. They were worried about what will happen if their data leaks somewhere. That is why the convincing the business owners is really important. It's not like that you take your device, go and inspect somewhere and collect the data, because all these data collections were based on the relationships and connections with the facility owners. So this one is really important. And in this slide, I want to talk about the summary of the limitations. The first one is possibility of sensitive information leakage by transferring the data to a centralized server. As I said, it can jeopardize the reputation of the business owners. The cost of data transfer and storage, need for more computational power. And the last one is data collection, we know is challenging. That is why the second aim of my project, my PhD, is to improve the safety and cleanliness assurance while assuring client data privacy. So how we can do that? Federated learning. There is a new paradigm in machine learning named federated learning. In the classical method, classical analysis, you go collect data, bring your data to your computer, and you analyze it. But in federated learning, instead of transferring the data to your computer, you will send your model to your client's computer. Your model will be trained there, and trained model will be sent back to your server. Let's give you two examples. The first one is next word prediction in smartphones. So when you start typing a message on your smartphone, you can see some suggestions as a next word on your keyboard. This is based on federated learning. The companies like Google, like Apple, they randomly select some clients. It can be one of us in this room. They send their model to your cell phone. They train their model based on your private text messages without touching your data, without directly accessing your data. Their model will be trained based on your private messages and sent back to the server and done. Again, another application is voice recognition system. The same is happening with Alexa, with Siri, with Google Assistant. When you're talking to your voice recognition system, sometimes they train their model, they send their model. The model will be trained based on your private communication with your voice recognition system. They train their model and upgrade their initial model. So this is two main applications they use for federated learning. There are several open source frameworks and software for implementation of the federated learning, like TensorFlow Federated, PyC, Flower, Fate, FedML. And we use FedML. FedML is a startup. We are collaborating with them. They introduced a flexible framework for implementation of the federated learning. And for this project, we use FedML. And there is just one term I need to clarify about that. I need to explain about that, which is aggregation algorithm. As I mentioned, the companies will randomly select some clients. Just imagine 1,000 clients. Send their model, the model will be trained, and the trained model will be sent back to their server. So the server will have 1,000 trained models. So they need an algorithm to combine all of them, aggregate all of them to update the initial model. This can be done by federated averaging. And federated, there are lots of algorithms, but federated averaging is one of the well-known algorithm for aggregation. It simply is a weighted average of all trained models. And they use the weighted average to give the opportunity to the clients with more data to contribute more to update the initial model. So for data set, for training and validation, we use 8 clients. We already collected that data from restaurant, institutional, kitchen. And we collected data from 2 more facilities. We use them as our external testing. And the total number of frames we did the analysis more than 91,000 frames. And here I want to show you how federated learning-based training works. In our case, we have 8 clients. So as I said, we need to randomly select some numbers of clients. And here in our case, we selected 4. We send the initial model to them. The model will be trained based on clients' data. After the training is done, they send back the trained model to the server. Then we have aggregation, use federated averaging. And then we want to know, so now what's the performance of our model? We test it on all clients. And then we report the average of accuracy, loss, or other metrics. And here we can see it's an accurate loss and accuracy. If the performance is acceptable, we are done. If not, we need to go to the next round. All this process, selecting clients, sending model, training, sending back, aggregation, is one round of communication. Then we go to the next round. Next round, again, select some clients and model. You know, we can repeat it until we reach to the acceptable performance. So this was how federated learning works. But our main goal is to identify the clean and contamination frames while we preserving their privacy. So for identification of clean versus contamination, we use MobileNet version 3, and we train on 8 clients, and we tested on 2 more clients, client number 9 and client number 10. And on the right side, you can see that on top is the model accuracy, the bottom is model loss, and x-axis shows the round. As can be seen here, for example, the round 1, we could achieve accuracy close to 55%. So on 20, we reached to 90%, and we trained on until we reached to 150 rounds to make sure that our model is stable. Then we tested on client number 9 and client number 10. The accuracy was close to 96 for client number 9 and close to 95 for client number 10. And for segmentation, again, we used deep leveraging 3+ for training and validation 8 facilities and tested on 2 facilities. And for client number 9, we could achieve mean OOU more than 91%, and for client number 10, close to 90%. And again, you can see here, for example, number 2, this is the model prediction, and this is annotation by a human expert. They just selected 4 areas as contamination, but here we have lots more areas can be seen in raw frames. And same is happening here for number 6. We have a tiny area here. They missed that, but the model could find it. We have lots of these examples. And now I want to talk about privacy and performance trade-off. So I got a really good feedback from one of my committee members, and we wanted to know at what cost we can have more privacy. Because all the project, the previous steps analysis was based on the centralizing analysis. We brought the data to a central server analysis without having privacy. But we wanted to know at what cost we can have more privacy. To answer this question, we consider 2 scenarios. The first scenario, we put data from 8 clients together in a centralized way, and we tested on 2 clients. We did for classification, also segmentation. The second scenario, we put data from all 10 clients together, and we report the accuracy and mean and OOU. Because by putting the data, all these 10 clients together, we can achieve the maximum performance out of our model. And let's talk on the figures. The top one, it shows classification, privacy, performance trade-off. The blue color, it shows the federated learning output for client number 9. it's about, and it's 95.84. So it's with privacy. And the orange one is when we put data from 8 clients together without privacy. It's about 0.5% increase. And the maximum performance out of this model can be 97.81. It's around 2%. So in my point of view, losing 2% to have more privacy, so it's worth it. And same for segmentation. Segmentation for federated learning, the blue one is 91.23. And for 8 clients, 93.21, and the maximum is 95.87, which is around 4%, 4.5%. So losing 4.5% on OU. So I believe it's worth it to have more privacy. And we finally reach to the conclusion. For the conclusion, the assurance of cleanliness and sanitation are ongoing challenges in food industry. Fluorescent imaging technology combined with deep learning can improve the level of safety and cleanliness assurance. And we know, we talked about that. The companies and institutions are concerned that using new technologies can increase the privacy risk and also leak of sensitive information. To answer all these questions and concerns, first we designed 2 experiments for food safety assurance, for food safety and cleanliness assurance. We used several deep learning models to improve the contamination detection and identification, detection segmentation. And also we designed an experiment using federated learning to not only improve the cleanliness assurance in the food service industry, but also to make sure that our clients' data are safe and secure. And for future direction, as I said, deep learning-based methods are data hungry. The more, the better. We need to collect more and more data. So we are going to expand our database. And also we are going to solve the data annotation bottleneck, because data annotation is a time-consuming and it's a really tedious work. And we are going to use self-supervised learning. This can be it's a new method in machine learning. It can be a solution. It doesn't need labeled data to train the model. So we are going to test that out as our future direction. References and publications. I got 4 journal papers from my PhD, and the last one is the equal contribution on that, and also 7 conference papers. Also, I was involved in several other projects with different departments. Some of them was hobby projects, So 6 journal papers out of that, and also 5 conference papers. And here, I would like to thank, first of all, my advisor, Dr. Tavakkolian. I really appreciate everything you have done for me, Puyar, because he helped me a lot during these years. Actually, I was leaving the UND, and he is the reason now today I'm standing here and defending my PhD. And he's not my advisor. He's like my older brother. Thank you again. I would like to thank my committee members, Professor Reza, Dr. Durafshan, Dr. Liang, and Professor Petros. Thank you a lot, because you gave me really good feedback, comments and feedback. So it shaped my project and also my presentation. Thank you. And I know this is the 3rd time I have presented this work for you. So sorry about that. And I would like to thank Safety Aspect, the company CTO, Dr. Wasifim, for giving me the opportunity to work on the real world project, because it was really interesting to work on a real problem. And it's an amazing feeling when you work on something and finally you can see the output on a real product. So thank you, Fertosh. And also I would like to thank Nick Makinen. Nick helped me a lot for revising the manuscript. We sat together several days, several times to respond to reviewers, to revise the manuscript. So he helped me a lot. Thank you, Nick. And I would like to thank my wife. So without her, I couldn't be here. And honestly, I was not interested in continuing my education. She encouraged me and pushed me to get my master's, but I believe she pushed me really hard, because now I'm defending my 2nd PhD. So she needs to stop me. And thank you, my family. I would like to thank my family. And I would like to thank my friends, my lovely friends. They are here. Thank you all, Ramtin, Vida, Mahsa, and Sora. Thank you so much. And thank you for attention.